This is lesson 1.1, periodic phenomena. All right, so throughout this semester in PreCalc, we'll be studying trigonometry, and specifically we'll be studying what's called periodic functions. So these are functions that repeat themselves over and over and over again. So we need to talk about what that is. This will be a quick intro lesson. Let's dive into what periodic means. So following along the top of the notes, it says as input values increase, so as I plug in bigger and bigger numbers, if I plug in 1 to a function, and then 2 to a function, and then 3, and so on and so forth. If the output values of the function demonstrate a repeating pattern over successive equal length intervals, we have what is called a periodic relationship. So we're going to add that to our notes right now. This is a periodic relationship. Another word to describe this would be cyclical or a cycle, right? Uh, I know that's a really wordy definition. All I want you guys to do, and if you have a highlighter, I highly recommend you get one out and you add this to your notes. All I want you guys to focus on is the fact that if you look at this wave function here, it's a nice, pretty wave. If I highlight just this portion right here, that portion repeats itself over and over and over again in both directions. All right. That's all a periodic function does. Okay. Cool. It says if we have the graph of a single period or cycle, then we can construct the graph of the periodic relationship. The following graphs show one period of a periodic function. All right, and we'll come back to that word period in just a minute. It's the same as cycle. We'll define those in just a sec. But right now, we should practice with that concept. If I was to just give you one cycle of the wave, could you recreate the rest of the graph? That's all we're talking about here. So yeah, totally we can do that, right? If I know that this is a pattern that repeats itself, I want to add a repeating wave over here on this side, on the right. I also want to add a repeating wave over here on the left. Okay, cool. So right here, if I start at 0, it looks like I reach the peak of my hill up 3 and over 2 units. So everyone go 1, 2, 3, over 1, 2. So right here, if I start, it should repeat that same pattern. So I should go up 3, over 2. This should be the top of my next hill. Just like that. And then from the top of the hill, it looks like it goes down 3 units and over 2. So I should do that, down 3 over 2. It looks like I'm going to run off the page a little bit, so it should look something like that. All right, cool. Now, you can also run this backwards. So if I go back the other way, all right, this is going to continue down to the bottom of this hill. So once again, if I start here on the axis, to get to the bottom of the hill, I have to go down 3 and over 2. So let's do that. I'm going to go down 3 over 2. This should be the bottom of my hill. And then it looks like it's going to pick back up and go up 3 over 2. Right there. And then it's going to continue up 3 and over 2. Something like that. So it's going to curve and then start going up, and then it's going to reach the top of the hill again. So once again, as long as you have one cycle of a wave, you should be able to recreate the rest of the function, because this function is just a pattern that repeats itself over and over and over again. Now, periodic functions are not always pretty waves like this. Sometimes they're a little more rough, a little more jagged, like this one over here, but same deal. If you have a pattern that you know repeats itself, you should be able to recreate the rest of the graph. So right here, if I'm reading this left to right, like I'm reading a book, I'm going this way, I know I'm going to go down 2, up 2, down 1, up 1. So I'm going to repeat that one more time. So I'm going to pick it up here where I left off, and I'm going to go down 2, up 2, then down 1, then up 1, just like that. Okay, and then same deal. I can run this backwards in the other direction. Now be very careful. When you're going backwards, you have to run the pattern backwards, all right? Be careful not to go down 2 here because then you're creating a mirror. You're not recreating the pattern. Okay, so if I'm going to go back this way, I need to read this pattern backwards. So starting here, I go down 1, up 1, down 2, up 2. All right, cool. So pick it up right where I left off. I'm going to go down 1, up 1, then down 2, up 2. Okay, I can draw that way better. Oops. All right, here we go. Down 1, up 1, down 2, up 2. All right, slightly better. If you make your notes far prettier than mine, please do so. But you get the idea. It's this jagged edge relationship repeated over and over and over. Okay, cool. Now let's define what a period or a cycle actually is. It says the period of a function is the smallest change in x values it takes for the function to repeat itself. So again, if you have that highlighter out, let's go ahead and highlight that definition right here. Okay, so the period of the function is the smallest change in x values it takes for the function to repeat itself. In fancy math terms, we say the period of the function is the smallest positive value of k such that f of x plus k is equal to f of x for all x in the domain. Okay, all this means is that if I were to plug in a value of x, let's say 2, and I get a number, all right? I need to know what is the smallest value of k that's going to give me that same number as when I plugged in 2, all right? Here's a good example using one of the graphs to show you. Let's see. Let's pick a different color. Let's pick that color. Okay, maybe. There we go. All right. So in other words, if I pick any random point on this graph, let's say this one, all right, the next time I hit that point, okay, right there, this distance is k, okay? That's all this is saying. Very good. In fact, when we look at these next two examples, my suggestion to you, the easiest way to identify the length of the period for a function is to either count from peak to peak, so figure out what that distance is, or to count from valley to valley, figure out what that distance is. Either way will get you the right answer. So in blue, to do valley to valley, this x value right here is 0. This x value right here is 1/2. So to figure out what this distance is, I need to do 1/2 minus 0. I'm going to get 1/2. Okay? Same deal. If I do peak to peak, I should get the same exact value. So if I look at this x value right here, this is 1/4. And if I look at this x value here, this is 3/4. So k, the period, should equal 3/4 minus 1/4. And yep, that is also 1/2. Okay. So the period of this function is 1/2. All right. All right. Same deal over here. Now, in this one, we don't have enough of the graph to see the next peak or the previous peak. So we're going to count valley to valley here. So I need to figure out what is this x value. It looks like it's -4. And I need to count it all the way over to the next x value. It looks like it's 12. So I know k is going to equal 12 minus negative 4. Remember, minus negative, that turns into a plus. So this is 12 plus 4. That means the period of this function should be 16. Okay, very good. All right, moving on. Okay, back page here. It says periodic functions take on various characteristics of a function, such as increasing, decreasing, different concavities. We'll come back to that in just a sec. So I'm going to go ahead and underline that word. That's a weird one. And then we can recognize that any characteristics found in one period of the function will be in every period of the function. Basically, all that means is anything that we observe in one wave is going to happen in every wave because it just repeats itself over and over and over. So right here, it says below is one cycle or one period of a periodic function. I only have one wave. Use the graph to answer the questions. It says, is the function increasing, decreasing, or both on the interval 18 is less than x is less than 20? So imagine this graph looks like it only runs 5 x values. So we have 1, 2, 3, 4, 5. Imagine this graph was extended all the way to 18, 19, and 20. So all this means is I'm looking in between 18 and 20. So imagine I was to extend this pattern all the way over here. It's asking me between 18 and 20, am I going up? So increasing, remember this is going up. Decreasing, this is going down. Or do I do some combination of both? Do I go down and then up? Do I go up and then down? What am I doing? All right, now the easiest way to do this, there's a little trick that we can do. Yeah, you could actually draw it and figure it out, but the trick is we're going to figure out what the period of this function is first. So again, I can count peak to peak, and I can figure this out. All right, this x value right here is 0. This x value is 4. So I know the period, k, is going to be equal to 4 minus 0. That means the period is 4. Okay, that means every 4 steps, this repeats itself again. So if I were to draw the rest of this graph, picking up at the top of this hill, I would go down and then back up, and that would have taken me 4 more units. So I'd be at 8 now. And then I would go down and then up, and then I would be at 12. And then I'd go down and then up, and then I'd be at 16. And it would just do that for every 4 values over and over and over again. So the trick here is we're actually going to take each of these and divide them by 4 and see what we get, okay? If we get a whole number, all right, that means we are at the top of our wave. If we do not get a whole number, that means we're somewhere in between our wave, all right? And the reason this works is if you were to divide each of these by 4, this shows you how far along the wave you are. Okay, so after one step, I am 1/4 of the way to my next hill. After 2 steps, I'm 2/4 of the way, or halfway there. After 3 steps, I'm 3/4 of the way there. And after 4 steps, I am all the way there. I am 4 over 4 is 1. I've completed one whole wave. So what I can do is something very similar here. I can divide this range by my period, and if I get a whole number, that means I'm on top of the wave. All right. If I don't, looks like this one's not. I can look at I can look at the remainder, and I can figure out how far along the wave I am. Okay. So 18 over 4. Well, that is the same as 4.5 5. And then 20 over 4, that's the same as 5. Okay? Now, let's think about this for a minute. Let's rewrite this so that this 0.5 is a fraction. This is the same as 4.5, and 5 is just 5. Okay? So I know that this right here tells me how far along my wave I'm at. 1/2. I'm halfway there. In other words, I am at the bottom of my wave. So this is the bottom of the wave. This is the top of the wave. Okay, and now all you have to think about is to get from the bottom to the top. Did you go up? Did you go down? Or did you do some combination? Well, to get from bottom to top, I must have gone up. So I could say that this is increasing. Okay, very good. Let's look at the next one. Now it says, is the function concave up, concave down, or both on the interval between 31 and 33? Okay, now concave up and concave down. We're gonna draw a little diagram off to the side here, all right? So this right here is concave up. All right? The the wave is opening upwards, all right? Okay, this right here is concave down. Okay, the wave is opening downwards. Both would be something that looks like this. This is both. There's a part of it over here that's opening up, and there's a part of it over here that's opening down. Okay? All right, so same deal. I got to figure out, is this concave up, concave down, or both? Same trick. I'm going to go ahead and divide these by the period and figure out how far along my wave am I. All right, cool. 31 over 4. All right. 31 divided by 4. Let's see. What is that? That is 7.75 if you put it in a calculator, I think. Yeah, that sounds right. Okay, and then 33. What is that? That is 8.25 if you put it in a calculator. Okay. All right, so same deal. Let's turn these decimals into fractions to figure out how far along my wave I'm at. So this is 7 3/4 is less than x, which is less than 8 1/4. Okay, so if I look at my graph again, 3/4 of my wave, that would be right around here. Okay, and then I'm 1/4 of the way into the next wave. See how I've gone from 7 to 8? That means I'm on the next wave. So if we go back up to our picture, this would be like I've finished this wave and I've started to come down 1/4. So I've started to come down here. This is what we're talking about. All right. This is 3/4 of one wave all the way to 1/4 of the next wave. That means, look, am I concave up? Am I concave down? Or am I both? This looks concave down to me. So we're going to go ahead and put that. Okay. Now, last, is there a relative max, relative min, or neither at the point x equals 82? All right, so one last thought here. Let's do a green color. Okay, a relative max. This is a hill. A relative min. This is a valley. You guys should remember this from last semester when we talked about polynomials, okay? So I am looking, am I at the top of my wave? This would be a max. Or am I at the bottom of my wave? This would be a min. Okay, it looks like the top of my wave is every 4 steps. Okay, so 4 out of 4 steps. That means if I divide this by 4 and I get a whole number, that means I'm on top of my wave. I'm at a max. Okay, the bottom, the minimum, this is every 2 steps, or 2 out of 4, that's halfway across my wave. In other words, if I divide this by 4 and I get a number with a 1/2 on the end of it, that means I must be at a minimum, a relative minimum. All right, so I'm going to go ahead and do that. I'm going to say divided by 4. Well, that means x is going to be 82 divided by 4. I'm pretty sure that is 20.5. In other words, that is 20 and 1/2. And oh, look at that half. That means I am halfway through my wave cycle. That means I must be at the bottom of my wave. So this is a relative min or minimum. Okay, that I believe is it for this lesson. Really simple stuff when we're just looking at the picture. The formulas will start to get a little complicated, but as long as you can tell what a periodic function is, you're good to go. Good job.